Hello, welcome to a TE tutorial on differential equations. My name is Ken. I am the chairperson for the Tutoring and Engineering Excellence Program, sponsored by Tau Beta Pi at the University of Florida. So, for today's topic in differential equations, we'll be covering characteristic equations. So, we define a characteristic equation for the sake of this tutorial as an equation that expresses a portion of a linear, homogeneous, ordinary differential equation in polynomial form, such that we can perform algebraic manipulation of that polynomial to yield a general solution to that differential equation. So how do we apply this definition to solve differential equations? To do that, let's look at a second order example. So here we have a differential equation that is a times y double dot plus b y dot plus cy is equal to 0, where y dot and y double dot is the first derivative and second derivative of y respectively, and a, b, and c are assumed to be constant. So first, we have to make an assumption about what the solution could be. So for the sake of argument, let's assume that the solution could be of the form y is equal to e to the rt, where r is the roots to the characteristic equation that we'll find later on, and t is just our independent variable. We'll call it time. So now that we have an assumption about the solution to the differential equation, let's work with it. Let's take the derivative of it and the second derivative of it. So y dot should now be re to the rt, and y double dot should be r squared e to the rt. Which means now that we have an expression for y dot, and y double dot that we can substitute into the differential equation. So performing this substitution, we should get a r squared e to the rt plus b r e to the rt plus c e to the rt, all is equal to 0. So note that e to the rt is present in each of the elements of the differential equation now. So we can distribute out that e to the rt to make it into a more convenient form. So now the expression should look like this. E to the rt is now equal to, e to the rt is now multiplied by the expression ar squared plus br plus c, and all of that must be equal 0. So let's think about what this tells us. So for this entire expression to be true, one of these two elements must be equal to 0. But we know that e to the rt can never be 0 for all values of t. So that tells us for this entire expression to be true, the expression contained within the parentheses must be equal to 0. And this magical expression is our characteristic equation. So now that we have the characteristic equation, what else are we supposed to do with it? Well, if we find the roots of the characteristic equation, that means we can plug in those roots back into our substitution, and that should yield us a potential solution to the differential equation. So how do we find the roots? We use the quadratic equation back from algebra. So as you may remember, r is equal to negative b plus or minus the square root of b squared minus 4ac over 2a, where r is the roots of the second order polynomial. So we can use this and plug it into the expression for e to the rt, and that should yield us results. But an important thing to note is this element, everything under the square root operation, b squared minus 4ac, will yield different solutions. So for our first case that we'll consider, we'll assume that everything under this square root is positive. So we'll get two real distinct roots out of this expression. So with that being said, let's move on to an example problem. So let's look at the first case where we can apply the characteristic equation to solve differential equations. So for the first case, we have to consider when the characteristic equation yields real distinct roots, or if we're using the quadratic formula to find the roots of the characteristic equation, when the square root of b squared minus 4ac component of the quadratic equation, or the quadratic formula, is greater than 0. So, just to reinstate, basically, we want to consider the characteristic equation that yields real distinct roots, which we can call R1 and R2. So, for this case, we'll consider the example where we're asked to find the general solution to the differential equation of y double dot plus 7y dot plus 12y, which is all equal to 0. So, to solve this, first we have to ask ourselves, what is a general solution? So, within the differential equations world, a general solution means basically we want all possible solutions to this differential equation here. So now we need to ask ourselves, well, what is this differential equation? Well, we can deduce properties of this differential equations based on what we have here. So for example, we know that this entire expression is equal to 0. So if it's equal to 0, that tells us our differential equation must be homogeneous. We also know that we have a y, y dot, and y double dot. So that means, since y double dot is our highest order expression, that we can call this a second order differential equation. We also know that there aren't any x double dots or x dots in here, so we can say that this is ordinary rather than partial derivative. This is an ordinary differential equation instead of a partial differential equation. We also know this is linear because there aren't multiplications of the different derivatives of y with itself. So, just to sum it up, we know it's homogeneous, we know it's linear, we know it's ordinary, and those properties are useful in order to tell us what we can get away with while solving this equation. So we know that this is a second order differential equation, and we've seen an example where characteristic equations can be used within second order ordinary differential equations. So we're going to implement that method here. So first we have to begin with the substitution. We're going to assume that we can express y as e to the rt, right? So naturally, we'll take the derivative of y to get r e to the rt, and the second derivative of y, which is equal to r squared e to the rt, right? So let's take what we have here and substitute into the original expression of the differential equation. So y double dot will now become r squared e to the rt. Then we have plus 7 r e to the rt and plus 12 e to the rt, which all must be equal to 0. As before, each element has e to the rt in it, so we can distribute out the e to the rt to make it the expression into a more convenient form. So our new expression should be of the form e to the rt is equal to r squared plus 7r plus 12, all of which must be equal to 0. And since we know that e to the rt can never be 0, the characteristic equation here must be equal to 0. And since this is a second order polynomial, we can use the quadratic equation in order to solve the roots of the characteristic equation. So let's write that down. We know that the quadratic formula is of the form r is equal to negative b plus or minus the square root of b squared minus 4ac over 2a. We'll say that r1 is equal to negative b plus the square root of b squared minus 4ac over 2a. And we'll say that R2 is equal to negative b minus the square root of b squared minus 4ac over 2a. And finally, we'll say that a is equal to the coefficient of y double dot, which it is implied to be 1. We'll say that b is equal to the coefficient of y dot, which we know to be 7, and c must be equal to the coefficient of y, which we know to be 12. So with that in mind, all we have to do is substitute our a, b, and c expression into the expression for R1 and R2 to get the real distinct roots of the characteristic equation. So let's do that now. So R1 is equal to negative 7 plus the square root of 7 squared minus 4 times 1 times 12, all of which must be over 2 times 1. So solving for this, we get negative 7 plus 49 minus 48, all of which must be over 2. Which, when we take the square root of that, we get negative 7 plus 1 over 2, which means that it just becomes negative 3, right? So, let's look at R2. R2, more or less, must be negative 7 minus 1, right? Since the only difference between these two expressions is the plus and the minus of the square root element. So we know that it eventually boils down to negative 7 minus 1 over 2. So that's just negative 8 over 2, which means that our second root must be equal to negative 4, right? So now that we have the roots of the characteristic equation, where one root is equal to negative 3 and the other root is equal to negative 4, that means we have two potential solutions to the differential equation. So let's look at that. Look at that now. So using the first root of the differential equation, we know that one solution to the differential equation is of the form e to the r1 of t, which we can then say is equal to e to the negative 3 of t. But since we want to find the general solution, we want to find all possible solutions to the original differential equation, right? Now, e to the negative 3t is a solution to the differential equation, but we can find more solutions to the differential equation by simply multiplying this by an arbitrary constant. We'll call that constant c1, so that the new expression for the first solution to the differential equation, which we'll now call the first set of solutions to the differential equation, as c1 e to the negative 3 of t. So that's our first set of our first set of solutions to the differential equation. We can obtain our second set of solutions to differential equations by looking at r squared, the second root of the characteristic equation. So we know that the second set of solutions to the differential equation must be of the form of c2 e to the negative 4 of t, where negative 4 is the second root and c2 is an arbitrary constant just like c1. So now we have two sets of solutions to the differential equation. But unfortunately, we're still not done here. Like, even though we added the c1 and the c2 to these expressions to increase the amount of possible solutions that we're expressing, there's still one more condition that we need to consider. And that's the condition defined by the superposition principle, which basically says that another collection of solutions to the differential equation can be defined as a summation of these two expressions. So basically what that boils down to is that the general solution is an expression of y1 of t plus y2 of t, which means that the final answer, our general solution to the differential equation before us, is of the form c1 e to the negative 3t plus c2 e to the negative 4t. And this right here is our final answer, our general solution to the differential equation. And note that because c1 and c2 are completely arbitrary, we can define them as anything. For example, c2 can equal 0. And if it equals 0, that means we have the original y1 of t up here, right? Or y1 of t times c1. And then we can also say c1 is equal to 1, which means that we reduced this set of solutions to the differential equation to one single solution. So you can see how powerful this expression is right here. Like, we can have an expression for all possible solutions to the differential equation, or a particular set of solutions to differential equations, or one single solution to the differential equation, all within this one equation right here. Now, so that's an example of using the characteristic equation to solve a differential equation, given that our characteristic equation yields real distinct roots, which I'll remind you again is when this part of the expression of the quadratic formula that we use to solve the roots is greater than 0. Like, for the next case, and we'll consider what happens when this part of the formula is equal to 0. And then the next case we'll consider after that is what happens when this part of the quadratic formula is less than 0. But we'll save that for another video. Thank you for watching.